Es un placer presentar a André Guerra de la Universidad de Cambridge, que, que hoy nos va a hablar sobre Compensated Compactness, the hard space, and open mapping theorems. Te escuchamos, gracias.
Gracias. Thanks a lot for inviting me to speak here. Yeah, thanks, Mari, and nice to meet you online. Hopefully next time in person. So yeah, so I'm going to give in some sense a bit of an overview talk about several results that I obtained well a while ago now, actually. So in my PhD and mostly during my PhD. Um, a few years ago with several collaborators. So it will be mostly an overview of what we did, what are the questions, what we did about them, and kind of what remains open. I will also try to show some proofs maybe towards the end if we have time. So please interrupt me if there's something which isn't clear. And of course, feel free to ask any questions throughout. So let me begin by maybe describing what is the basic idea of compensated compactness, which is the first part of my title. So it feels appropriate to start there. So the starting point is something that I think you will know, which is that in general, if you take the product of a weakly convergent sequence, so if you multiply it with another weakly convergent sequence, then typically this doesn't converge. Okay, so even weakly, right? So this is a general fact, about sequences in Hilbert spaces, for instance, or Banach space. However, there are some circumstances in which the product of weakly convergent sequences does converge. So let me give you a first example. This is a very well-known example, which is due to Luja and Tartar in the early 1970s. And it's also a kind of a physically interesting example. So in this example, you take two sequences. So you take a sequence EJ. So these are matrix fields. So they go from Rn into n by n matrices. And you take a sequence Bj of vector fields. Again, they are defined on Rn and they go to Rn this time. Maybe I want to actually take both of them in Rn. So let me do it like this. Yes. So they are both vector fields in Rn. And let's say that Bj is divergence free and curl of Ej is 0. So Ej is curl free. And let's say that these sequences converge weakly. So the pair Ej, Bj, these are sequences which converge weakly to some limiting sequence in L2 locally, for instance. So let's say you have these things, then it turns out, this is what Luja and Tartar show, that if you look at their inner product, it converges actually to the inner product of the limit in the sense of distributions. Okay, so what are we saying? You see here you have the product, of course, this is the first entry of Ej times the first entry of Bj and so on. In principle, none of these entries, none of each term individually converges, but when you sum all of them, they do converge to the corresponding quantity evaluated at the limits. And that is true is related to the fact that Bj are divergence free and curl and Ej are curl free, so to speak. So one can think that these are kind of some version, let's say, of the Maxwell equations from electrostatics. So this is a predominant example of a case where you can indeed take products of weakly convergent sequences which converge. So let me show you a different example which is not unrelated. So this example is, I think, even a bit older. So it was known already to Mori, I think, in some form, and also to Reshetniak, also in the 70s. So in this example, I now take instead a sequence of gradients, so they are also curl-free. So these gradients will converge weakly in Ln, for instance, locally. So these gradients uj are maps. I'm thinking they are vector fields if you want from Rn into Rn. So their gradients are n by n matrices. And then you can show this is what I showed, that the determinant of these sequences actually converges to the determinant of the limit, again, in the sense of distribution. So this is, again, such an instant, right? The determinant is a polynomial. I mean, what is this expression, right? It's, again, a sum of products of entries of determinants of the uj. So this is another instance where you do have this. And of course, let me just note that in 2D, actually, both examples are the same. So this is very easy to see because you can write the determinant of du as a map, right? So this is just d1 u1, d2 u2 minus d1 u2, d2 u1. And we can actually write this as an inner product between d1 u1, d2 u1. So this is the gradient of u1, right? Scalar the rotated gradient of u2. Right? This is exactly what we have above. And you see now that this is the gradient of u1. So, it will be curl-free. And this is, in turn, a rotated gradient. So it will be divergence-free, right? If I take the divergence here, I get 0. So both examples are the same. So if you want a more general example, which actually encodes the above example. So this example was shown a bit later by Robin, Rogers, and Temple in 1987. So they show the following. So you take, so it's an example with differential forms. I mean, if you don't like differential forms, feel free to ignore this example. It's not relevant for necessarily very relevant for what comes next, but it's essentially a way of writing all of these examples. So you take a sequence alpha j I forms. So this will converge weakly in some space LP I. I'm going to assume that I have a certain number of forms. I don't know, let's call them L, and that the sums of the PIs is 1. So that they are in the right spaces. And moreover, one can assume that all of these forms are closed. So the alpha ij is 0. So this would be the analog of these differential conditions that we have here. Here, of course, this is also curl-free. So it is a condition like that, essentially. And so what they showed, which is a generalization of the above examples, is that if you take the wedge product of these differential forms, this converges weakly to the wedge product of the limit. Okay. So they also ask in this paper, so they ask, are all examples, whatever this means exactly, are all examples like this, essentially? Or are there other examples, right? So we started with simple example, two examples which seem, very similar to each other. This is a more general version, example 3. So they ask, are there other examples of quantities which can? So what is the takeaway here, right? The takeaway here is that you have certain nonlinear quantities. For instance, the determinant, for instance, the inner product, for instance, the wedge of forms. You have certain nonlinear quantities which are essentially products of things, and these nonlinear quantities are weakly continuous. They pass to the limit, right? Even when you just have weak convergence. So when you have these nonlinear quantities which nonetheless are weakly continuous, this is what is called compensated compactness. Compensated compactness. So the origin of the term and the idea of the term is that the lack of compactness, which it just means you just have weak convergence instead of having strong convergence, the lack of compactness is compensated by a suitable differential constraint, right? For instance, here these forms are closed. For instance, here you have some diff curl structure. So that is the idea. You have some differential constraint which compensates for the lack of compactness. And therefore you can actually pass to the limit in some nonlinear form. So there is another side of this story, which is called compensated integrability. You can guess maybe from the name what it means, but let me kind of motivate it. So something that one can ask, I think it's natural to ask once you've seen all of these examples, is you can ask to which space do these nonlinear quantities, so I emphasize, of course, they are nonlinear, otherwise there wouldn't be much to say. To which space do these nonlinear quantities belong? So let's again take an example. So let's take again a simple example, which is the determinant in 2D. And let's take a test function. So it's a test, it's a vector field from R2 to R2. And you can compute that, the determinant of the U, if you go back to this calculation that we did here, what are we doing, right? We've seen that you can write the determinant of the U as essentially the inner product between the gradient of the first entry with the gradient of the second entry, the rotated gradient. Let me write it like this. So, of course, I see a gradient. What do? I integrate by parts. I have compact support, so there are no boundary terms. So I integrate this gradient by parts, and I get U1 times the divergence of this guy. But as we saw, this is divergence free. So this is actually 0. So in other words, if you take a test function in R2 and you compute the integral of the determinant, you always get 0. And actually the same happens, it's easy to see if you do the bureaucracy. It's see that the same happens in all dimensions for the determinants. Even assuming only that so the correct assumption should be that this is integrable, this object, right? So essentially what you need to assume is that the U is in Ln of R. So what this means is that actually the determinant, so the determinant of, let's call it the Jacobian, right? The determinant of the gradient, this operator, it is an operator from the homogeneous Sobolev space into the space of certainly L1 functions, right? I mean, it will be an L1 function, but it is moreover a function which has 0 average, right? That's what we just witnessed. So it maps at least into L1 functions with 0 average. You can ask, is this somehow the smallest space that you can put here? And actually, no. So the answer is very interesting, and it's related to compensated integrability. So actually, this was discovered by Koifman, Lyon, Meyer and Semmes. And actually, it's very strongly inspired by a previous work by Stefan Müller. So this is in the 90s, in the early 90s, I don't know, 1999, 1991, 1992 maybe. So they actually observed that there is a strictly smaller space that you can put here. So they observed that the determinant actually maps, so the Jacobian maps this space into what is known as the Hardy space, which I will denote by H1 of Rn. So this is known as the Hardy space. So, I mean, okay, it is in the title of my talk, the Hardy space. I will maybe paradoxically not define it. Instead, I will tell you what it does, because it is more useful than actually the definition, which I think either you know it already, or if you don't, it will not be especially useful to see it. So let me instead tell you what it actually is. So H1 is, as I said, is a strict subspace of L1 functions with 0 average. Okay, it's strictly smaller. And it's really, the way you should think about it is as a harmonic analysis replacement of L1. Okay, so this is really the definition you should think. It's a version of L1 which works well for in harmonic analysis. So as you know, harmonic analysis does not like L1 so much. For instance, if you try to solve, Laplacian U equals F and F is in L1, U is not in W2, for instance, right? And another way of saying this is that, for instance, Calderon-Zygmund operators are not bounded in L1, but they are bounded. So another way of saying this, so okay, an example would be Calderon-Zygmund operators are actually bounded in H1. Another more PDE version, for instance, of saying this maybe would be that if you solve Laplacian of U, maybe let me write it like this. If the Laplacian is in H1, then actually U is in W2. So also for PDEs, if you know that somehow you have a structure which is in H1, that's very useful. You can actually do endpoint estimates. And, this has many applications in PDE, in harmonic maps, in fluid dynamics. I will not really overview this here, but you can imagine, I think that's a very useful fact. So actually, what Koifman, Leo, and Meyer and Semmes is that, the determinant has this additional property. It has a special structure, and it maps into a very nice space from the point of view of harmonic analysis. And actually, they observe this not just for the determinant of the gradient, but they observe this essentially for all of these examples. So they observe this also for the Diffker lemma. This inner product is in the Hardy space, similarly in example 3. So let me just write this down. So actually, also in above examples, let's write it like this: nonlinear quantities are in H1. And this is called, one way of thinking about H1 is that at least locally, you should have some kind of slight improvement in integrability, maybe by a logarithm. This is not exactly true, but it's a nice way of thinking about it. So, so this is called, this is why hence the name of this section. This is called compensated integrability. Okay, so then there are kind of two natural questions. So there are two natural questions asked by Koifman, Leo, Meyer and Semmes by so I will just say by CLMS. So let me write them here. So the first question is whether this is a coincidence or not. So the first question is, are compensated compactness, and compensated integrability the same? We just saw that they do coincide in these examples. And another question is kind of, what is the range? So this is the question we were trying to vaguely address here. So what is the range of the Jacobian and the similar operators? So for instance, they ask specifically, is this a surjective operator between these spaces? So that would really tell somehow this is the best, in some sense, space you can put there. So of course, surjective would be a stronger statement than that. But so these are two very natural questions, which in some sense are about having a deeper understanding of these examples, which are quite fundamental. So the rest of the talk, in some sense, is to tell you kind of what we know and what we don't know about this question. Is it clear so far? I mean, is there any question? Maybe it's a good time to ask if there are. Okay. If not, then please.
No, that's okay.
Okay. Okay. So So another question is, okay, so there are maybe many ways of answering these questions, depending on how general you want to be. I will describe here, in some sense, a framework which is very general, but one could also say maybe the least general of all general frameworks, if that makes sense. But I think it's, from my point of view, it's maybe it has the correct, well, maybe correct is a strong word, but it has an appropriate level of generality for applications in PD at least, which is what I am at least personally interested in. So this framework actually is due to, it's again an old framework. It's essentially due to Ra and Tartar in the 70s again. And it was also kind of popularized, perhaps, and in a very interesting work by Fonseca and Muller in 1999. So the framework is the following: you take V and W. So these are finite dimensional vector spaces. You take some collection and now you define, okay, maybe it's best to write it straight away. So you take an operator A. So this will be a linear homogeneous differential operator. So with constant coefficient. So it's an operator of the form A alpha D alpha. All derivatives have order L. Right here I use multi-index notation, so it's homogeneous. And A alpha, it has constant coefficients. So A alpha is these are linear maps between V and W. So matrices, if you. This operator has a symbol, right, associated with it, which is exactly the same, except that you replace derivatives with Xi. So Xi would be a vector in Rn, let's say. So the idea is that this operator is encapsulating some basic physical property of the system you are interested in, right? So if you go back to the beginning, the operator would be, for instance, a diff curl operator, or here it would be the curl of a matrix field because these guys are gradients. Here it could be the operator would be the exterior derivative, and they act always on different vector spaces, right? Here it acts on the fields are n valued. Here they are Rn by n valued. Here they are valued in spaces of differential form. So it's useful to have these vector spaces V and W. But in all of the above examples, and actually many other examples, like in linear elasticity, incompressible fluid mechanics, and so on, you typically have operators like those above, so homogeneous constant coefficient. Of course, you could also consider something more general, but this is often good enough for applications. And so, more importantly than this, we are going to assume two conditions. The first condition, I will not really precise what it is, but it's essentially a condition that A spans V, whatever this means. So this is just a condition which ensures that you don't have a trivial operator. Let's say it's a non-triviality condition. So far, what I mean by this is that A is non-zero. Okay, I mean, an operator which you could have is the zero operator. This operator would be very uninteresting from our point of view. More generally, you could have operators which only see certain parts of V, right? For instance, they don't see vector fields which take values, if you write V in a basis, E1 up to En, they don't see fields which take values in the last element. Right? That would also be, in some sense, like saying that A is zero in a certain part of V. So we really want a non-trivial operator. So this is just a condition which there's really no point in precising. It's just to say that you have really an operator which sees the whole of V. Otherwise, you shrink V in order to guarantee this condition. Okay. So it's really not. It's really a condition just to avoid an interesting case. But more importantly than this non-triviality condition, more importantly, we assume that the rank of A of the symbol. So this is the symbol operator, right? We assume that this is actually constant for all C. So here C, should be non-zero, let's say. So for all C non-zero. This is called the constant rank condition, and this is really a non-degeneracy assumption. Non-degeneracy assumption. So it is at the same time both a strong and a not so strong condition. It is a strong condition in the sense that it really guarantees you have a well-behaved operator. It is not such a strong condition in the sense that in practice it's verified by most examples you could care about. It's verified, for instance, by all the examples I mentioned, by the div curl, by the exterior derivative, by just the curl, by for instance, by the operators which appear in linearized elasticity and so on. So it is verified in many examples, but it is a condition that we have to deal with and which is fundamental. Actually, we really don't know how to do essentially anything in the absence of this condition. So assuming this framework and these conditions, which, as I say, encapsulate the previous example, let me tell you the first theorem I want to tell today. So this is the theorem with Bogdan Raita a long time ago, in 2021, or maybe it feels like a long time ago. So the theorem is simple to state. So you take a quantity f, and we can assume very little about it. Let's just assume that it's locally bounded and measurable. And we assume that it's not affine, right? So I said at the start, we are interested in nonlinear quantities. So f is one of these quantities. It's not an affine quantity. Then the following, so the theorem says that, maybe let's write it like this. So the theorem says that the following two statements are equivalent. So the first statement is essentially compensated integrability. So you take, so for any vector field, okay, so the statement should be like this. For any vector field V, which is a test vector field, so it goes from Rn into V, and it's A-free. So it satisfies your differential constraint. Then for any such vector field, f of V is in H1. So f has this hardest space integrability, this kind of higher integrability, in some sense, is compensated integrability. This is the first statement. The second statement is instead the compensated compactness statement. So it's kind of for every sequence, for every sequence Vj, which converges weakly star in L infinity locally, which again should be A-free, right? So A of Vj 0 for any such sequence. F is weakly continuous. So f of Vj converges weakly star to f of V in D prime. So it is really equivalent. It's not really a coincidence that in all of the previous examples we had, this is a general fact. Compensated integrability and compensated compactness in the setting we have here are really the same thing. If you have a nonlinear quantity which satisfies one, it satisfies the other, and conversely. Moreover, we can say a few more things. So let me say a bit more about what we can say. So we can moreover say that then if this holds, let's say if this holds, maybe it's the best way of writing it. So if this holds, then okay, we can say the following. So we can say that f is actually a polynomial. So it's again not a coincidence that right. So in these examples we have above, either it's a determinant of polynomial or a quadratic polynomial, or here it's also polynomial. It's, if you expand it, it is essentially like a determinant. So it's multilinear if you want. So it is not a coincidence. They are always of this form. So f is a polynomial, and actually we can say something about its degree, which is also sharp. So the degree is the minimum, is at most the minimum between n and the dimension of V. Moreover, we can compute explicitly. If you give me an operator, I can tell you, I can solve some algebraic equations. I can compute explicitly the set of f's for which this holds. So it's there is some algebraic characterization of these polynomials. And moreover, F is of the form of example 3, is of form of example 3. If you interpret it correctly, so let's say in suitable coordinates. I mean, there are some identifications you have to do, which are, there is no point in really precising it. But essentially, you can think that indeed the answer to this question asked by Robin Rogers Staples is yes. All examples are basically of this form, if you interpret of this form correctly. So this is essentially the statement. First part is maybe stated slightly more precise than the second one. So let me just say what is kind of a crucial point here. I mean, I don't really want to tell you maybe too much about the proof. It's also somewhat long, and okay, there are many parts as you see. But let me tell you kind of what's the basic idea. So a crucial point here is really a previous paper by my co-author. So it's Bogdan's first paper by Raita a few years before, in 2019. So he showed the following. He showed that let me call this non-constant rank conditions star. So he showed that star implies, actually it is equivalent, but it implies that the kernel of A, of the symbol operator, if you want, is really the image of B, of Xi, for every Xi non-zero, and for some, so potential operator B. So B is again like A. So it's a homogeneous operator of different order in general, do not have the same order. Which can be written as above for some suitable linear maps between some other vector spaces. So essentially, what Bogdan showed is that, again, if you go back to our list of examples, all of these operators have a potential operator, right? I mean, this is especially clear maybe in the last example where, the potential operator of the exterior derivative is the exterior derivative acting on forms of 1 degree lower, right? And that's exactly what's happening in all of these examples, right? The potential operator of the curl is the gradient. The curl is a potential operator for the divergence and so on. So essentially, you can always, if you are a little bit like in the situation in the Dahem complex, in general, you cannot choose these operators to be of the same order. There are examples, but it is a bit like that example. And in particular, using this, so this is one of the things I did with Bogdan. If you use the existence of this potential operator, you can use this. So we use this is one of the main points in the proof is we use this to prove a Hodge decomposition, or Hodge or Helmholtz, depending how you prefer to call it, but Hodge decomposition. So this decomposition asserts that if you give me a vector field in LP, and here P should be between 1 and infinity, then you can write V as BU plus A star W for some U and W, and this so it will be exactly like the Hodge decomposition now for these generalized operators, and as in the Hodge decomposition, it comes with suitable estimates. So there are some harmonic analysis estimates here. So you can bound B of U by the LP norm of V, and you have also some estimate for A star of W by some actually negative Sobolev norm of AV. So these estimates, they are not so important exactly what they are. I just want to tell you, to write them down. So essentially, it is a decomposition which you control very well, exactly like in the usual Hodge decomposition setting that you are all familiar with. So it is similar to that, and using this, this is kind of one of the starting points for the proof of this theorem. We also had some follow-up works also with Matthew Strecker, where one of the things we did is we clarified to which extent you can relax the constraints of a V being A free. You see here there is an estimate where you you're not seeing my cursor for some reason. Right here at the bottom there is an estimate in terms of AV in some negative Sobolev space, and actually you don't really need V to be A free. You just need to control these in suitable spaces, and we kind of clarified what are the best spaces you can take there. But these are maybe more technical refinement. So anyway, this is somehow the main tool for the proof, and of course it relies crucially on the constant rank condition to construct such a B, such a potential operator B, and also the constant rank condition is crucial to prove these estimates. Otherwise, they are also basically not true. So they said it plays an important role. Okay, so this is in some sense is an answer to question 1, right? Remember we had these 2 questions. Is it the case that compensated compactness and compensated integrability are the same? And the answer is yes. In this framework, indeed, they are the same. So, okay, so since we answered this one, and we still have a lot of time in the talk, let's try to discuss the second question. So the second question is about the range of these operators, in particular, whether they are surjective. So this brings me to the last part of my talk, which is about surjectivity and open mapping theorems, also the last part of my title. So let me rephrase again question 2. Let me call it question 2 prime. So the question would be, and this is what actually CLMS asked. Take the Jacobian, right? So in W1N from the homogeneous Sobolev space to H1. So is this operator is the Jacobian surjective? And there's actually a conjecture by Ivanich in Ivanich's conjectures. So he gets as an answer conjectures that the answer should be yes. So this was conjectured in 1995. I think he conjectured it in 2 different papers, but I think this is the earliest occurrence. And I should note, and this is related to a paper of one of my collaborators, so it's actually important, very important in this question. It's important that you take the homogeneous. So I emphasize, maybe let me write it like this. It's very important that you take the homogeneous space in this question. Otherwise, the answer is no, actually. So you have to take the homogeneous space. So this was shown by Lindberg, Solly Lindberg, in his first paper, actually, in 2017. So this is the question. So I want to, this is a very difficult question. So I want to actually ask a simpler question. So we want to ask a simpler question. And the simple question is related, of course, to open mapping theorems. Open mapping theorems, the theorem you know from functional analysis, is of course related to surjectivity. It gives you equivalent conditions for surjectivity of linear operators. So let me recall the classic open mapping theorem by Schauder. So the statement is that you take L to be a linear operator, operator between Banach spaces, and the open mapping theorem gives you, as you know, equivalent conditions for surjectivity. So it says that L is surjective if and only if L is open. Okay. So let me frame this since it is an important statement. Okay. So let me just, before maybe getting into what we can or cannot do, let me maybe give you a more PD way of thinking about it, which I prefer, and I think it's conceptually interesting. So a more PD way of thinking about this, or of stating this, is that the following 2 statements are equivalent. So the first statement is really a statement about qualitative solvability. qualitative solvability. In other words, it's a statement that for every f, there is a u such that L of u equals f, right? So you can solve the equation LU equals f without saying anything else. But the second statement, openness, okay, seems like a topological condition. It's really, in some sense, one can think about it as an analytic condition, which instead gives you quantitative solvability, right? So openness means that for every f, for every datum f, there is a u such that LU equals f, so you can solve the equation, and moreover, the norm of u is controlled by the norm of f uniformly, right? I mean, this constant here, maybe let me not use this notation, but this constant here is uniform for all f. It doesn't depend on f or on u. In other words, if you can solve, so what the open mapping theorem tells you is something I think quite surprising, right? It tells you that if you can solve a linear equation, you can actually always solve it with estimates. It also justifies, in some sense, the method of a priori estimates to prove existence, right? If you are trying to solve linear PDE, it's not a miracle that you prove a priori estimates and then this will give you existence. It's actually a posteriori, because of this result, it's actually necessary. If you can solve a PDE, you must solve it with estimates. A linear PDE, you must solve it with estimates. I think this is a very deep fact, which so it's a very deep fact about linear equations. So it's not really, once you see all of this, of course, we are mostly interested in nonlinear equations. So a question that you can ask, and that was asked by Rudin in 69, is the following question. So is there a version of these results? Is there an open mapping theorem? Let's not even talk about general nonlinear operators. Let's think about the next simplest class of operators, which will be the class of multilinear operators. For multilinear operators. And unfortunately, the answer is no. So the answer to this question is no. So this was answered by Paul Cohen, the Fields medalist Paul Cohen in 1974. And actually, I think he has an infinite dimensional example, if I remember correctly. But actually, there are even counterexamples in essentially R6. So multilinear operators on R3. Yeah, if you want to think about it like this. And this was shown just the year after by Horowitz in 1975. So Rudin's question, it's I think a beautiful question, but it's essentially completely false, even in finite dimension. Maybe at this point you probably give up, and I guess that's this kind of line of reasoning died. So the answer which I propose here, it's a different answer. Is an answer which is that partial differential operators are not any operator. They are very special operators. Of course, we do not come really from functional, we come from PD. So we are not thinking just about operators on monospace, we are thinking really about partial differential operators on function space. So they have other properties. And so the answer we could show, and this is joint, this was a joint work with Lucas Koch, and again, Sauli Lindberg. So yeah, it was published in 2023. I think it's slightly older. Yeah, this is the publication date. So what we could show is the following. Let me give you a simple statement of what we could show in the case we are more interested in, which is the determinant of the gradient, also the Jacobian. By the way, this is of course a multilinear operator, right? The determinant is multilinear, so it is an operator in the setting of Rudin's question. Of course, not all partial differential operators that you are interested in are multilinear, but this is such an operator. So we could show that indeed there is an open mapping theorem for the Jacobian. So in other words, the Jacobian from the homogeneous Sobolev space to H1 is surjective if and only if it is open, okay, which I will write in a PD way. So again, as I wrote above, so the PD way would be that for every datum f, there is a solution u of the equation, determinant of the u equals f, and moreover, the norms, of course, are controlled, in the only way which makes sense, which is this one, the scale invariant way. So again, this constant C is uniform. It doesn't depend on maybe it depends on n. This would be so. The Jacobian is a multilinear operator which does satisfy the open mapping theorem. Okay, so even if it fails for multilinear operators in finite dimensions. So how much time do I have left? Maybe it's a good time to ask.
About 50 minutes, 20.
Okay, perfect. This is perfect. So let me show you actually the proof of this theorem because it's not so difficult and I think it's interesting. So let me show you the proof. Okay. I think it's surprising that you have a functional analysis result which is true in some sense in infinite dimensions and is false in finite dimensions. So I want to explain why this. It's not really, in some sense it is about that, but it's not really. It's the very specific structure. So let me use somehow a more functional analysis notation. Let me call T our operator. So this is an operator between X, which is the homogeneous overlap space, and Y, which is the Hardy space. Okay, so let's suppose, of course, the second segment implies the first, right? I'm assuming already I'm surjective. So let's show that surjectivity actually implies a priori estimates. So let's say that T of X is equal to Y. So we are going to follow the proof to begin with of the classical open mapping theorem. So this means that I can write Y as a union over L, an integer, let's say, a countable union of those datum F in Y in the Hardy space for which there is a U, for which I can solve the equation TU equals F. This is the equation I want to solve. And moreover, I control the norm of U by L. So this just means, I can certainly write it in this way. There is a U, and I just find the L for which that is true. So these sets here I will call KL. Those sets. Okay, this is the union of sets. So let's note, and this is related to the beginning of the talk. We saw at the beginning that, just remind you, right? This is the starting point of the talk is that the Jacobian is weakly continuous. Actually, this convergence is in the sense of distributions, but because of a priori estimates, it becomes also weak star convergence in the Hardy space. It's easy to see. So the Jacobian from X to Y, so T, is an operator which is weakly star to weakly star sequentially continuous. And therefore, the sets KL, this is a set of solutions of the equation. So this set is weakly star closed. It's a bounded set, so it's also closed. Now, as in the usual open mapping theorem, this is the deepest part of the proof. You apply the bare category theorem, right? The bare category theorem tells you that there is an L, an integer L, such that, the bare category theorem essentially tells you one of these sets must have non-empty interior. So you can find an L for which the set KL has non-empty interior. In particular, it must contain a ball, right? So there is a ball around BR F0, around some F0 in the Hardy space, which is contained in KL. It's just what the bare category theorem does. So it suffices to show, actually, that BR of 0 is contained in KL. Right? Why is this? KL is a space where I can solve my equation with an estimate. My operator is homogeneous, right? The determinant of the gradient. This is a homogeneous operator. If I multiply U by lambda U, it becomes lambda to the n times the Jacobian of U. So if I can solve the equation, I can always scale it down and then scale it up again if I want. So it is enough to essentially find solutions with estimates in a small ball around 0 by homogeneous. Okay, I think that's clear. So let's try to show this, right? So let's take F with a small with norm less than r, so f is in BR0. Then what we do is we look at the element f0 plus f translated, and translate it by k, let's say. So k, k will be an element in the integer lattice, for instance. So, of course, these norms are all translation invariant. So this guy has norm, this guy translated guy still has norm less than r. So this is certainly in BR of f0. Therefore, by what we've seen, right, BR of f0 is contained in KL. Therefore, hence, there is an element uk for each k. There is a uk such that you can solve the equation t of uk equals this datum. So f0 plus f plus k, and of course also with our estimate. So now we use so now we perform the following calculation. So we compute. So we are going to translate uk. So we compute t. Remember, t is the Jacobian of a function. So we compute t of uk translated by minus k. Of course, this is an operator which has constant coefficients, so it commutes with translations. You can either translate it before or after. So this is the same as computing the Jacobian of u and then translating it. Okay, I think this is also pretty clear. This should be uk. And okay, now I see what it is from above, right? So this is just f0 translated plus f. But now send k to infinity. These are translations of some fixed f0 that you have. It's a function in the Hardy space. You send it to infinity. This converges weakly star. You are sending it off to infinity. So this is going to converge weakly to f as you send k to infinity. Of course, again, the norms of all of these translations, they are the same. So they are also bounded by f. So maybe, let me also emphasize here that this equality here is really because t is commutes with translations. Commutes with translations. As it is a partial differential operator, PDO, PDO with constant coefficients. Okay, so what we see is that right. I mean, if you see this data f0 blah blah blah, this translated data, it does so because we have solved it with an estimate. This translated data here is in KL, right? By definition of KL. But this set is weak star closed. But we thought since the Jacobian is weakly star continuous. So also f, its limit, is in KL. Right? This is exactly what we wanted to show at the start. You take a point in BR0 and it is in KL. So this is the end of the proof. So the proof, it follows to some extent the proof of the open mapping theorem, but it uses, of course, the very special structure of our operator. So what is really needed? Okay, once you look at the proof, you understand that there are only essentially two things that you need. You need that, as I emphasized, that the Jacobian is a partial differential operator with constant coefficients. You need that this operator is weakly star to weakly star sequentially continuous. Maybe continuous. And maybe a third thing which you need, which is also implicitly here, is that you need to work over Rn. Right? It is important that you are sending these translations to infinity. You couldn't really do this in a bounded domain, right? There would be a problem if you do that. But essentially, what we proved with Lucas and Saldi is that essentially, if you have these conditions, very informally speaking, then under these conditions, essentially you can, revisit this proof. So under these conditions, the same proof works. So this means that there's actually a nonlinear. So let's say there is an there exists an open mapping theorem for nonlinear partial differential operators with constant coefficients over Rn. So examples would be, okay, maybe you are worried about the second condition. This condition, so they don't need to be multilinear, right? They are really, the multilinearity is actually not important. So this condition is either satisfied if you have a very special operator like the Jacobian, which has this kind of compensated compactness property, or if you are essentially in a subcritical PDE, in an energetic sense. So examples would be, for operators for which you can apply this, would be subcritical NLS, for instance. But also you can actually apply it to the equations of incompressible fluid dynamics. So you can also apply this to incompressible Euler or Navier-Stokes equations. So it is slightly more general than that. It's not actually trivial to apply to these equations, but it can be done. So, okay, so in the process of trying to remember where we started, right? We wanted to answer this question. Is this operator subjective? We provide the characterization of it, but we did not answer it. And in fact, let me maybe end my talk by saying that, in fact, the original question about the range of the Jacobian remains open, actually. So we have this characterization and we hoped to use it and to our advantage, but we did not succeed. So maybe it's something for the future. Yeah. So let me stop here, and yeah, I will be happy to answer any questions you may have.